Greetings and welcome. In this section, we are going to work on problems from question 2, Physical Sciences Paper 1, DBE 2022. This is a June paper. Now, this question 2 is based on mechanics, which refers to Newton's laws of motion. We know that we have got 4 laws that we need to be able to state and apply, which is Newton's first law, Newton's second law, Newton's third law, and Newton's law of universal gravitation. And then, so question 2 is based on Newton's laws of motion. So let's get into the question. We have got question 1.2.1. Okay, question 2, part 1. The question reads as follows. A man faces difficulty while swimming in a dam. During the rescue operation, an inflated tube attached to a helicopter by a rope is dropped from the helicopter. The man of mass 70 kg, so we are given some data here. Mass is 70 kg, holds onto the inflated tube of mass 4 kg while the helicopter is flying horizontally at a constant speed, that is highlighted there. An average frictional force of 300 Newton is exerted on the main tube combination while they are dragged horizontally along the surface of the water by the helicopter. The rope makes an angle of 50 degrees with the surface of the water as shown in the diagram below. Assume that the rope is inextensible and massless and the water of the dam does not flow. Question 2.1. State Newton's first law of motion in words. So Newton's first law of motion is stated as follows. A body will remain in its state of rest, will remain in its state of rest, or motion at constant velocity, or motion at constant velocity, unless a non-zero net force or resultant force, unless a non-zero net force acts on it. So that's how you state Newton's first law. Basically, what is he saying? That an object will remain unmoving, will remain wherever it is. So it will remain in its state of rest. So state of rest means that it is not moving. So if you leave an object wherever it is and there's no force applied to it, the object will remain in a state of rest. It will not move, okay, unless there's a force that acts on it. A force is a push or a pull. So that is the first part. An object, a body, will remain in a state of rest. Or it may be moving. So he is saying that a body will remain in its state of motion. So it will remain moving at a constant speed, at the same speed, unless there's a force acting on it. So Newton's first law refers to the property of a body which is called inertia. Okay. Inertia. So inertia is not a force, it's just a property of a body. So this is the inertia is the property of a body that enables it to resist any change to its state of motion. It is a property of a body that enables it to resist, any change to its state of motion. Okay, so meaning that if an object is at rest, there's a tendency that if you want to move it, it will resist that change in its state of rest, or it may be moving. So if you are going to stop it, it is a tendency of resisting that state of motion. So for example, when the brakes of a moving vehicle are applied to bring it to a stop, so the occupants of that particular vehicle, the force that is not acting on the occupants, so there's a tendency that the occupants will continue moving forward. That's why we've got these safety belts. So that property is coming from Newton's first law of motion. Okay, so but the question here is just asking us to state. So you state it as given here: a body will remain in its state of rest or motion at a constant velocity unless a non-zero net force acts on it. Coming to question 2.2. Question 2.2 is asking us to draw a free body diagram of the main tube combination when they are being dragged. Okay, so a free body diagram is simply a diagram that is showing all the forces that are acting on an object. Okay, so in a free body diagram, the object is represented by a dot. So represent it with a dot. Okay, and then all the forces acting on the object are drawn pointing away from that dot. So we are going to draw a diagram showing all the forces acting there. Now I will just draw the forces here, explain them here, and then we'll draw the diagram on the other side of this page here. So we'll find that here the forces acting on the combination of the man and the tube. The first obvious force is the tension in the rope. Okay, so it's being pulled, and that force is acting at an angle of 50 degrees. Okay, so that is the first force that we have. Secondly, the man has got a mass, so there is gravitational force. Anything that has got mass above the Earth's surface has got a gravitational force. So there is a gravitational force that will act downward. So there will be a gravitational force here. Okay, it's a gravitational force which is weight. Okay, and then also the combination is also floating. So there is a force that is applied by the surface of the water. That force is the normal force that acts perpendicular to the surface. So there's a normal force. And then there's another force that is resisting the motion of the combination, of the main-tube combination. That force is the frictional force, which is given here. So frictional force will always act opposite the direction of motion. So the man is moving to the left, and then so frictional force will act towards the right. So that is FK. So now we have 1, 2, 3, 4. These are the 4 forces acting on the object. So this represents the free body diagram. So you find in most cases that if they are given 4 marks, you must realize that mostly there are 4 forces that are required. So let's draw this one, a neat diagram. So our free body diagram, so we have our dot here representing the combination of the man and the tube, and then our gravitational force acts downward. Okay, so that is our FG. We can call it W. And then there is frictional force to the right. There is normal force acting up, okay, that is N. There is a tension acting in that direction at an angle of 50 degrees. So we'll label it as T, and then we can just indicate that it is acting at 50 degrees. Okay, remember that is 50 degrees. So those are the forces that are acting on the object. So that answers that question. And then we have got question 2.3, asking us to calculate the tension in the rope. So as the main tube combination is being pulled, how much is the tension in the rope? Okay, how much is the tension in the rope? So in this case, we are going to use Newton's second law of motion. Newton's second law of motion is summarized by the formula F net is equal to ma. F net is equal to ma. The net force acting on an object is equal to the mass of the object times the acceleration of the object. Okay, it's one of the laws that you also needed to state. We'll come to that part at a later stage. Now here we are going to use the fact that we are given that the helicopter is moving horizontally at a constant speed. So the term here, constant speed, or the phrase constant speed, refers to the fact that the acceleration is zero. The object is not gaining speed. So constant speed or constant velocity means that our acceleration is 0 meters per second squared. So the object is not gaining any speed. So when acceleration is 0, now since our net force is mass times acceleration, so we are going to multiply the mass by the acceleration. So this means that we are going to have our net force being equal to 0. Okay, so our net force is going to be equal to 0. Now, in this case, now we will use this equation here, this statement, to calculate the tension that is in the rope here. Now, what we are going to do is to express the net force as a sum of all the forces that are acting on the object. So to apply that principle, we must be aware that the net force acting on an object, it is the sum of all the forces that are acting on the object, especially those forces that are acting parallel to the direction of motion. Okay, so the object is going to the left in this case, so it's going to the left. So there must be a force that is pulling it to the left. Okay, that force is part of the tension in the rope, the applied force. We call it the horizontal component. The symbol that we use for that is Fx. So the horizontal component of that force. Okay, so this force is acting parallel to the direction of the movement of the object. Another force that is acting parallel to that is the frictional force. So we are not going to consider the normal force and the gravitational force. It's only the frictional force and this other force that is acting in that direction. Now, to be able to determine that force, okay, we are going to use the fact that, let's say we have got our tension, okay, our force tension is acting in that direction. Okay, so that is the direction, and it is acting at an angle of 50 degrees. Now, when a force is acting at an incline, at an angle like that, okay, that force can be expressed into two components. We can resolve it into two components. There is the horizontal component, okay, of the force, which we will call the Tx or the Fx. So there's a horizontal component, and then there's also a vertical component, okay? There's a vertical component to that force. The vertical component, we'll call it the Ty, okay? You can call it Tx or Fx or T. We are using T here because we are using the term tension. So the angle formed between the horizontal component and the vertical component is 90 degrees. And here is our 50 degrees. So the tension is applied at an angle of 50 degrees to the horizontal. So now what we are going to do is to be able to derive a connection between this horizontal component and the T, the tension, which is the question that we are asked to calculate here, the tension in the rope. Okay, so we are going to use trigonometric ratios. So here we'll realize that we have got a right angle triangle. The force, the length of this side T is acting as the hypotenuse, and the Tx is our adjacent. So if we take Tx divided by T, that is giving the ratio adjacent, because this is next to 50 degrees, over hypotenuse, that will give us a ratio cosine of theta, theta being the angle, which is 50 degrees. So this is going to give us cosine of 50 degrees. So if we are going to make Tx the subject, so we are going to have Tx is equal to T multiplied by cos 50. Okay, so we are going to use this one in a moment. So our horizontal component can be expressed in terms of the angle, the force that is acting at an angle, which is this, the T. Okay. Now let's come to the net force. So our intention here is to be able to break down the net force in terms of the forces that are acting parallel to the motion of the object. So as we said here, we have got the two forces, Tx acting to the left and the frictional force to the right. So what is always advisable to take the direction in which the object is moving as your positive direction, because when you add forces, you use the vector addition. Vector addition means that you are going to use the direction, okay? So here we are going to say our horizontal component is Tx acting to the left, so the left is positive, so our Tx, okay, plus the other force acting is the frictional force plus F. This is the net force, the sum of all the forces. This is equal to 0, okay? And then we are now going to substitute the values of Tx. So our Tx, as we found here, is T cos 50. So I'm going to write T cos 50, because the question is asking us to calculate tension and not Tx. So T cos 50. Now frictional force is acting opposite the direction of motion, so that is a negative 300. So this will give us a 0, okay? As a result, we take 300 to that side, so we have T cos 50 is equal to 300 divided by cos 50. So we are going to get T is equal to 300 over cos 50 degrees. Okay, put that one in a calculator. Okay, so I have it here, 300 over cos 50, that will give us 466.72. okay, that is 466.72 to 2 decimal places. Okay, so that gives us the tension in the cable or in the rope. Now coming to the next question. Okay, the question is asking us to choose from the following whether the force is going to increase, decrease, or remain the same. So it reads 2.4. Let's put it here, 2.4. It reads as follows. How will the answer to question 2.3 change if the helicopter accelerates while dragging the man? The frictional force and the angle between the rope and the surface of the water remain the same. Okay, so we are given the fact that now the helicopter is going to accelerate. The helicopter, in other words, the acceleration is now going to increase. So will this tension increase, or will it decrease, or will it remain the same? We have to give a reason for that. Of course, for us to answer the question whether it is increasing, decreasing, we have to have a reason first. So let's explain the reason here. Now, the reason we have also to apply Newton's first law and Newton's second law rather. So Newton's second law says F net is equal to ma. So initially, when the helicopter was moving, the acceleration was a 0. Okay, the acceleration was 0. Now, when the helicopter is accelerating, which means the value of the acceleration is greater than 0. Okay, so it can be any value that is greater than 0. Now, from this statement, you find that the net force is directly proportional to the acceleration, meaning that when the acceleration increases, okay, the net force will also increase. So which means here we are going to have a case where the net force is going to increase. So when the net force increases, what will happen to the tension? The tension will also increase. So our reason here, just to answer the question here, the answer therefore is that our tension is going to increase. So our option is to say increases. Okay, why is it increasing? The reason being that the net force also has increased because the net force has increased. Okay, now how is it that when the net force increases, then the tension will increase? Okay, you can just make a mental calculation here. So if coming back to 2.3, if our acceleration is now a non-zero value, now let's take a number greater than 0, which can be 1 meter per second squared or 2 or 3. So you will find that when we substitute it in the formula F net is equal to ma, okay, our net force is no longer going to be a 0. Okay, it's going to be a value that is greater than 0. Now, assuming that we have got a value greater than 0 here, so if we substitute it as we have done here in this formula, so we are going to take the 300, the negative 300 to the right. So you'll find that the value of t cos 50 is going to increase because it's going to be 300 plus another additional value that we have here, which is not a 0. So basically, we are not going to divide 300. We are not going to divide 300, but we're actually going to get a value that is greater than 300. So as a result, when we divide by cos 50, we will have our tension increasing. So that is the reason why when the net force increases, the tension will also increase. So our tension is going to increase as the helicopter accelerates. Okay, so that explains the value, the answer to that. Coming to the next part of the question, it says that in another rescue operation, the inflated tube of mass 4 kg is dropped from the stationary helicopter and it strikes the water at a speed of 16 meters per second. So we also given some piece of information here. There's a mass of 4 kg, that is the inflated tube, and then it is going to be dropped and it strikes the surface of the water at a speed of 16 meters per second. The tube sinks vertically downwards into the water to a depth of 0.8 meters per second and then rises to the surface. The rope hangs loosely. Calculate the magnitude of the average upward force exerted on the inflated tube while it is sinking. Assume that the average upward force is constant for the motion. We are also going to use Newton's second law, again formula, which is F net is equal to ma. Okay, we'll come to that one, but we're gonna deviate a little bit here because we are given some information. The rope is dropped, okay, and it strikes the surface of the water at 16 meters per second, and then it is sank to a depth of 0.8. Now, this information that we are given here is allowing us to be able to calculate the value of A. Okay, we know our mass. We are dealing now with the mass of the tube, which is 4 kg. So the mass of the tube is 4, so our m is 4, and then we need to calculate our acceleration, and then we'll come to the net force at a later stage. So what we have here is the fact that we are given a case where we have got the tube striking the surface of the water. Okay, the speed at which, or the velocity at which it strikes the water, we can take that one to be our initial velocity. So our initial velocity is 16 meters per second, okay, downwards. And then it is going to sink to a depth in the water, okay, it is going to sink to a certain depth. So at a certain instant, the tube is going to come to a stop before it rises back. Okay, so as it sinks, the speed is decreasing. So there's an instant where it will sink into the water no more. So at that instant, we consider to be the final velocity. So our final velocity will be 0 meters per second. Okay, and then we are told that it sank to a depth of 0.8. So that 0.8 is representing our displacement, which is delta x or delta y, which is 0.8. Okay, so this combination of variables will allow us now to be able to calculate the acceleration. We are going to use the formula v squared final is equal to v initial squared plus 2a delta x. Okay, it's one of the equations of motion. We know that we have got, I think there are five equations of motion. First one is v final is equal to v initial plus a delta t. Okay, the second one is v final squared is equal to v initial squared plus 2a delta x, which is the one that we have used here. The third one is delta x is equal to v initial delta t plus half a delta t squared. Then the fourth one is delta x is equal to v final plus v initial over 2 everything multiplied by delta t. Now you don't have to worry much about this one because these equations are given in your formula sheet or your data sheet. So the reason why I'm listing here is why You might be asking, why did I choose this formula? Okay, given the information that we are given, the data here, we are given initial, final, and the delta x. So we are not given the time. Actually, we are supposed to have 5 variables, okay, which is v final and v initial, time, and then there is acceleration, then there is a delta x. Okay, 1, 2, 3, 4, 5. So you'll find that everything else has been given. We are given the final, we're given the acceleration. Acceleration is what we are going to calculate. We are given the displacement, but time has not been given. So that's why we couldn't use this one. So this one, we can't use this because we are not given the time. We can't use this one. We are not, we don't know the time, unless you can first calculate that time and then substitute. It's a possibility, and then this one. So that's why we are using this one. Okay, so now there's a certain section where we will explain the use, why do you need to choose this equation and leave the other and do the rest. Okay, so in this case we are going to use v squared final is equal to v I initial plus 2a delta x. Okay, so coming to that, back to this question, so we are going to say now, what is our final velocity? Is 0. So we square that one, that is 0 squared is equal to, okay, initial, that is 16. The initial velocity is 16 squared plus 2a, okay, times delta x, which is 0.8. Okay, and then we just simplify here. We've got a 0 is equal to 16 squared, that is 256, okay, plus 2 times this one, this is 1.6 times a, okay, divide there, okay, take this one to the side, that is negative 256 is equal to 1.6 a, okay, and then we divide it by 1.6, so our a is equal to, okay, let's put that one in our calculator. So that is a 256 divided by 1.6. Okay, what do we get? It's a 160. Okay, so it's going to be negative. So because we are dividing by a negative here, so it's going to be negative 160, because our 256 is that meters per second squared. Why is it negative? Because the object, as it accelerates down, it is reducing speed. Okay, so we found our acceleration. Now we are going to come back to the net force. So let me write it here. So our net force is equal to ma. Now we are also going to break down now the net force, because the question is asking us to calculate the average upward force, because as the tube is sinking into the water is thrusting it up. Okay, there's an upward push by the water particles. So that is the force that we want to calculate. So let's draw another free body diagram of what is happening here. So if you take the tube as a dot, so what are the forces acting there? One, we have got gravitational force. Okay, that is our Fg. And then we have got force upward, which is the thrust of the water, which is the Fa. That is what we need to find. Okay, so there are only two forces that are acting parallel to the direction of motion here. Okay, of course our tube is sinking into the water, so that is downward. So we are taking down as positive. So to break down the net force, we are going to say our F net is equal to Fg. Okay. Now this Fg is being opposed by the applied force minus Fa. This will be equal to mass times acceleration. Now Fg is the weight. So weight is mass times gravitational acceleration. The mass of this is 4 kg. Okay, so we are going to substitute here 4 kg. 4 into gravitational acceleration is a constant, which is 9.8, minus the applied force will be equal to mass. Again, the mass of the object is 4 into acceleration, the acceleration which we've just calculated here, which is negative 160. Okay, so multiply 4 by 9.8. Okay, so 4 by 9.8. Okay, that will give us 30 something, 39.2. Okay, so this is a 39.2. So 39.2 minus applied force is equal to, this one is going to give us a negative 4 by that one, that is negative 640. Okay, and then take this over to that side. We've got a negative Fa is equal to negative 640. 39 will be that one, that will be negative 679. Okay, 0.2. So the negative will cancel out, therefore our Fa will be equal to 679.2, which gives us the force, the average upward force that is exerted on the inflated tube. Okay, so that brings us to the end of this question. This is 17 marks, and the last part is 5 marks. Okay, thank you for watching. We will see you in the next video. Bye.